This is going to be a bit of a departure from what we saw so far, very technical talks. This is a very different kind of cryptography that we're going to be doing here, and in a much more applied context. So privacy preserving and decentralized contact discovery. This is joint work with Alberto Sonino from Miston Labs, Filip Jovanovic from UCL, and Kobe Gherkin from Geometry Research. So, as I said, we're going to be talking about identity-based cryptography, which I don't think has been covered at previous ZK summits, so that's going to be quite fun. And we're going to use that to bootstrap decentralized social apps, and I'll explain what I mean. So we'll first go through some motivation. What do I mean by contact discovery? What does it mean to do this privately? And what is the threat model we're working under? Then we're going to look at sort of a related work section, good attempts that fall short of our privacy desiderata. Then we're going to go over Arke in two parts. Firstly, a high-level construction, hopefully everyone can follow that one, and then a cryptography, which hopefully everyone can follow as well, but this is the fun part. And then quickly a few other applications for the construction and some warnings on what not to do with it. So let's start on a little journey. The year is 2020X, and in this year we can create anonymous blockchain accounts from our email address. Pretty cool. We can prove in ZK that we own a specific social media handle. And we can also build end-to-end private messaging and payment apps. And this is all really cool, and this hopefully shouldn't sound too foreign to most people in this room, and that's because this is actually happening today. A lot of these things, blockchain accounts from email addresses, there is a talk today about this, Aptos Keyless. ZK proof ownership of social media handles or even email addresses, you can do this with ZK email, and I think they're presenting today. Messaging and payments app, we've seen already. Great. So now, my question to you is, are we ready to build the next generation of social apps? And this is kind of my crude answer of, we'll build a privacy-first social app. We won't have a mechanism for users to find their friends on this app. And because it's private, well, it's really hard to find people. And so suddenly users can't socialize with their friends and are just not going to use the app. So this is the same reasoning is explained a lot more eloquently by Moxie Marlinspike back in a 2014 article called The Difficulty of Private Contact Discovery. And so he notes that most software today is social. Even privacy-enhancing technologies are social. And that these things only have value proportional to the people that use them. What kind of network is using this? And so he says, well, for our app to be useful, we need to access an existing social graph. And that's what we mean by contact discovery, especially because in the context of Signal, the social graph they tap into is mobile phone numbers, so your contacts. So a bit more concretely, again, we consider a user joining Signal, and they want to know who in their contacts is also using Signal. So the problem sort of kind of looks a bit like this, right? We have a set of contacts, a set of all Signal users, and what is the intersection? Turns out we need a bit more, because knowing that my friend is on Signal is great, but I also need their public key to do some cryptography there. I also need to know where to send my messages, like physically, where should they go? So we need this intersection and some extra information. Now, if we want to generalize this beyond Signal and phone numbers, we could use other identifiers like emails or you want to contact your ex-followers. And it would look a bit like this. So we have users, they have an existing identifier. This could be their email, their phone number again, or some Twitter handle. And they have a new ID, which here in this example, I'm using what looks like some kind of Bitcoin, like blockchain address. So maybe you've used ZK login or Aptos Keyless, and you've linked your email to an address. Now the question is, how can a friend who knows my email find my sort of keyless account? So we again have friends in my old graph. But on the right, we have users of this new graph, and I have this as a dotted line because there might not be an existing set of all users. In the Signal example, you sign up to Signal with your phone number. Signal knows, all right, all these phone numbers are registered. With Aptos Keyless or ZK login, all these mechanisms, no one knows who's registered. So this set on the right here might not exist. We also need kind of a mapping. In the Signal example, my contacts have phone numbers. Signal has registered phone numbers. Great, phone numbers in both cases. In this example, we have an existing identifier, some kind of handle, and a new identifier, which might not match. So we also need this mapping. What does it mean to do this privately? And I kind of have 3 layers of privacy here. The first one is nobody should learn my contacts. I shouldn't have to reveal who my friends are to find them. The second one is I should be able to filter who finds the link between my old ID, my email address, and my new account, my blockchain account. Right? Like if I do ZK login, Athens keyless again, I'm spending so much time, so much effort hiding this link between my email address and my blockchain account. Why would I then reveal it here? The third layer is kind of hard mode. It's not even revealing who signed up to the new social app that we're building. Against who do we want to defend? Well, anyone, right? Users of the app, my own friends, maybe they want to know if I'm friends with a specific person. So dishonest users, and the service itself. Great. So now that we have a notion of the problem at hand, and so the requirements, I want to look at some related works. The first one is the one actually most apps use right now. It's just upload all your contacts to a server and do the matching and the clear. So this is what WhatsApp, Telegram do. The pros of this approach is that it works. The cons is you have no privacy whatsoever. And even worse, you're sort of centralizing something that wasn't centralized. So the mobile social graph, for example, I have my contacts on my phone, but no one else has them. As soon as I upload them to WhatsApp, they can start drawing out this graph, connecting the dots between my contacts, your contacts, and everyone. So they suddenly have this almost proprietary info that no one else has. So basic approach, terrible. Second approach is private set intersection. I've been drawing these sets and this little question mark. So at some point you're like, all right, are we going to find the intersection of these sets? The answer is no. But I'll tell you why in a second. So private set intersection is a family of protocols where we compute, as it says, the intersection between 2 sets. Private means we don't reveal either set. We have protocols to do this in the unbalanced case, so like when the set on the right is much bigger than the one on the left, which is kind of the case of contact discovery. And it's pretty practical, although Signal refuses to use this because they think it's too much work, and they'd rather sort of emulate this with trusted hardware. The pros is that contacts remain private, by definition of how these things work. The cons is that you do need this set on the right. You need someone to know the list of all users, and you need someone to know the mapping from their old identifier to the new one. The other problem is you can actually scrape this. You can show up as an honest user with what you claim to be your contacts, get the intersection, but in fact, you didn't show up with your contacts. You showed up with a list that you're enumerating, trying to find out who is signed up or who isn't. This actually happened to Facebook back in 2019, and there's a paper that goes over how Signal, WhatsApp, Telegram have a really hard time defending against these attacks. So PSI, cool, but not enough. So the last approach, we're saying, all right, if this second set on the right is decentralized, well, we're going to have to do this in a decentralized manner. So that's what I'm calling peer-to-peer contact discovery. And the idea here is that users will take it on themselves to send messages to each of their contacts to say, hey, here's my new identifier on this new social app. This is what we do with Arke, and this is what other concurrent works are doing, UDM and Pudding. The pros is that we can achieve all our privacy goals. The cons is that now the users have to do a lot more work. They take it upon themselves to send these messages, and they also have to check and receive these messages from their friends. All right, so how do we do this peer-to-peer contact discovery? We start with users know their friends' identifiers. This is great, I have my contacts. And I want to exchange a message privately in a way that's undetectable. It seems like I haven't moved the problem forward at all, right? Because I was saying, oh, I was trying to contact friends, and now I'm still trying to contact friends. But we can work through this, and we'll go from exchanging a message. we know that we can do encryption to exchange a message privately. That's great. As long as I have a shared secret, I can do encryption. How do I get a shared secret? Well, some more cryptography, I can do a key exchange. So as long as I know someone's public key, we can find a shared secret, and then we can do encryption. So we're happy. The question is, how do we do this final link from someone's identifier to their public key? So one of our concurrent works, UDM, just publishes this mapping. And that's fine, because the public key reveals nothing. It's just specific to the contact discovery scheme. And then what matters is the message you're exchanging. It does fail at what I was calling hard mode privacy, because it does leak who is registered and who isn't. What we are doing is we say your identifier is your public key. So that should strike you as a bit weird, because it is. And this is where this identity-based cryptography comes into play. So if your identifier is your public key, then we need to somehow derive your private key from the identifier. It can't be derived just from the identifier, otherwise everyone could do it. So it needs to be identifier and some randomness. And that's what we'll see next. How do we do this? Just very briefly, the reason why I'm bothering to do a key exchange and then symmetric encryption is because we actually want to exchange a message over a public message board without being detected. And so that will require some extra work. And that's why having a shared secret is nicer than just encrypting directly. So this is our system. This is what it looks like. We have sort of 4 phases. First is a setup phase, where your users interact with a discovery service, they prove that they have their identity, and they receive a corresponding public key. Private key. Yeah. Then once they have their private key and they know their contact's identifier, i.e. their public key, they can do this key exchange locally. Then having done the key exchange, that was the little thing we were looking at earlier, you can write to this bulletin board, encrypted, and read. So we're going to go through this sort of bit by bit, cryptographically, and open these black boxes. And hopefully I'm also going to convince you that this identity-based thing isn't too crazy, and it is actually secure. So, identity-based non-interactive key exchange. So we read this as ID night because it's a bit of a mouthful. They assume a trusted third party. So red flags all over, but in 3 slides we're going to get rid of that trusted third party and we're going to be happy. Formally it's defined by 3 algorithms. Setup, which outputs public parameters and a secret key to go to the trusted third party. We have this extract algorithm that takes the secret key and an identifier to extract the private key for this identifier. And then we have this shared key function, which using one user's private key and someone else's identifier derives a shared secret. So importantly, it has to be shared. So it doesn't matter if I take the secret key of ID and then the public key of ID prime, or if I take the secret key of ID prime and the public key of ID. I should be getting the same secret. The security property of these systems, not going to dwell on this too much, but it's that this shared key should not be distinguishable from a random value, which also means you shouldn't be able to compute it. Great. So how do we build these? There's a construction from 2000 by Sakai, Ogishi, and Kasahara. Before I explain this, a quick reminder on how pairings work. We have this function E, where you can put in 2 things, G to the A, H to the B. This one is a symmetric pairing, but we work also with the more common asymmetric pairing. So what you can do in the symmetric case is you can flip them, the G and H, that's great. And the pairing has this property that it's bilinear, so these exponents can be taken outside of my E function. Leave this in a corner and back to the construction. So setup looks a lot like our usual setup algorithms. We sample a random number as our private key, and the public parameters is some kind of public key. Now we get into the interesting stuff. Extract. The secret key for the identifier ID will be a hash of the identifier to the master secret key. The shared key between ID and ID prime will be a pairing of the secret key of ID with a hash of ID prime. If we write this out, I can replace skid with this h of id to the MSK, take the MSK out, and we have this nice e of the hashes to the master secret key. And if I worked from the other direction, the same thing would happen. Cool. So now how do we get rid of this trusted third party? Right, like, otherwise we haven't done anything. If we have a trusted third party, the system is useless. So the first thing I want you to notice is that extract looks like this. It's a hash of something to the power of something else. And the question is, does this look familiar? Like, have you seen this somewhere? Hopefully, for most people in this room, it's yes. This is a BLS signature. So your private key is a BLS signature. And now the question is, how can we make BLS signatures in the setting where no one knows the signing key? Again, hopefully we should know this. It's a threshold BLS signature. So how do we get rid of the trusted third party? Well, we thresholdize this master secret key. And everything else works perfectly, right? Still, I need to get a signature on my identifier, so I don't want to be revealing that identifier to the system. Again, how do I get a signature on a message that I keep secret? We also have a cryptographic name for these things. These are blind signatures. So we can use blind BLS signatures and a proof of knowledge that you do own the identifier and that you do know the identifier that was blinded to effectively hide your identity. Sorry, let me go back. This means that we fully get rid of the trusted third party. We instead have a signing committee, and this committee learns nothing about who you are. Lovely. So now users can get their private key. They can use this private key to get a shared secret. How do they exchange a message without being detected? And that's what we're calling unlinkable handshake. I think there are a few different names going around for this thing. It's not really defined. So we have our shared secret. We can use that to derive a bunch of random things, including an encryption key, like a symmetric encryption key, some tag that we're going to use to identify our ciphertext, and we can encrypt whatever message we wanted to send. So remember, in this case, the message is my new identity on this new network. And then we can publish this tag and ciphertext onto a public bulletin board. The tag is sort of pseudo-random, so you can distinguish it from something random. The ciphertext is also pseudo-random if we're assuming that we're in the ideal cipher model, which is very close to the random oracle model. In fact, they're equivalent. And so this is what the bulletin board would look like. Just a bunch of tags associated to ciphertexts. And to an external observer, this means nothing. But to someone who knows a tag ciphertext pair, they know that this is a message from one of their friends. So to read a message from a friend, I just go up to the bulletin board. I also derive the symmetric key and the tag. I take down whatever I need, and I can decrypt. One thing that could leak a link between people is access patterns to this bulletin board. So we do require that every write and every read is performed through an anonymity network. So you could use Tor, right? And a new identity every time you go and read. And that's kind of it. We now have this four-stage process where, first in the setup, users obtain shares of their private key from these discovery nodes. And although this is drawn as like, one entity, this is actually a committee of signers. I should also mention that this committee of signers, we can set the threshold to be whatever we want. It doesn't have to be honest majority. It could be like n out of n if we wanted it to be. There is a usability trade-off, obviously, because users will have to query at least the threshold. So that's step one, setup. You get your private key in this way. You reconstruct the private key locally. Then you can do the key exchange, which is one pairing per friend. And then you simply use this key to derive an encryption key and a sort of identifying tag. Great. So what else can we do? I've been talking about the context of contact discovery, but in fact, what we've built here allows us to secretly exchange an arbitrary message with someone I know. So you could send like a transaction through this, a pre-authorized transaction. And you're effectively by doing this, paying a friend who hasn't even signed up to a system, but who does have some kind of ID that you know, their phone number, their email. So this is actually a great onboarding mechanism. You can maybe use this as an airdrop where you send these transactions and people don't have to claim and go and see you and be like, hey, please give me my airdrop. The transaction is already there for them to pick up. And again, it's a very similar logic to the onboarding logic. And in fact, this idea of using identity-based encryption to pay someone based on their identity is also used in this UTT paper, which I've linked here. Another angle is maybe in games. You could have games where teams are set up at the beginning, and teams have to remain secret for some reason. Say you're playing Mafia or Werewolf. This could be a way, maybe, game developers, let's see, to have players establish contact within their team without revealing who is in what team. If you have other ideas, please do get in touch, because, yeah, we'd be very happy to collaborate. Quick words of warning, what not to do. Do not use this as your main communication channel. This is slow. You have to send messages to this message board through Tor and then download them through Tor. You don't get push notifications either. You have to go and check for messages. So this is not great as a communication channel. It's great to exchange a first message with someone you would otherwise never be able to communicate with. What else you shouldn't do is do not send important private information through this. This isn't as secure as other means of communication in the sense that you don't have forward secrecy. So with Signal, there's a key rotation mechanism, which means if your old keys get compromised, your new messages are fine. With this, it's not the case. If the master secret key or the shares get compromised, if your key gets compromised or if your friend's key gets compromised, your messages will be leaked. So don't send private keys, but instead do send addresses, public keys, ephemeral secrets, things that will allow you to bootstrap a secure forward secret channel. With that, a few references and some concluding remarks, which is that we saw what contact discovery is, we discussed related work, and we saw our construction that uses this identity-based encryption and the handshake. In the paper, we do a lot more, and we explain how to build this bulletin board. You could use a blockchain, you can use way cheaper consensus mechanisms, and in fact, fully avoid consensus. We also talk practical considerations like access control to the message board, spam prevention, how to verify that you're getting the right keys, all that is in the paper. We have the all-important security proofs, of course, and we have experiments. We ran this for a few days over 10 geo-distributed locations, and it's quite fast, and we think it can actually sustain the traffic of something like WhatsApp. That's it for me. Thank you very much.
Okay. Fab. Great, thank you very much. We'll move on to any questions. Yep, we've got a hand up over there. So there are mics on the seats. If you could just grab that and just press on, a little button, and fire away. Are our Q&A mics on? Hold on, don't worry, I'll run one to you. It's always the tech, right?
It's always the tech.
Is that one working? There you go. Have mine.
Thank you. Nico, what a great talk. What a great project. Thanks a lot. Really nice slides. Really, really cool. Really cool work. I had a question about two things. So the first thing was you said there's some cons in that the users have to do all of this work, but it seems like the application can do it for the users behind their back really easily. Is that fair to say?
That is fair to say, yes.
So if you integrated this in Signal from the user perspective, I think it's totally fine. That doesn't seem like a big con, right?
With the difference that your phone is now going to consume a lot more power, right? Whereas you would send, so the way Signal does it is you send your contacts into a TE. So you send it and the workload is done remotely. Here you'd have to compute one pairing per friend. You'd have to derive these keys, send messages, and your yeah, your client-side app would have to constantly sort of check for new messages on the message board.
I see. Okay. Oh, good to understand those overheads. And at some point, when you talked about the blind threshold signing protocol, you said that you would want the proof of ownership of the ID, which kind of hints to me that you might need to employ a general purpose snark to, reveal the pre-image of that arbitrary hash function, right?
That's correct, yeah.
And in what type of applications do you think you would need to prove ownership? Like a Signal, such an application?
So the blind signature has this weird thing that if you want your security proof to pass, you suddenly need some parts of your system to know the identifier.
Not just the hash, but...
Not just the hash, the actual identifier. And the way we got around that is by having a proof of knowledge so that we can have these extractors get the ID and then use that within our reduction.
But I thought for BLS blind, you can prove security without such a...
You can, but I'm not sure you can show... Essentially, we're trying to avoid impersonation attacks. I shouldn't be able to go up to the signing committee with your identifier, ask for signatures, and get your private key. So I need to somehow show that the identifier that's blinded corresponds to the identifier in my proof of knowledge, my proof of ownership of an identifier. Right?
Good. Okay, that makes sense.
Yep, lovely. Thank you. Any more questions? Oh, yeah, one at the back. Do you want to test your mic?
That might work? Yes,
Yeah,
it does.
great.
Thank you very much for the talk.
Pleasure.
The bulletin board, it seems like the growth of the number of entries there is quadratic in the number of users or in the number of something. How big does that get in your experiments, say, or in your projections?
So this is part of the practical considerations that I was talking about at the end that we don't talk about here. We break up the bulletin board into epochs of, say, like 1 week. And at the end of each epoch, we can clean out entries that have been used. Actually, we clean out everything, and then users have to re-upload. But yes, you have to sort of manage this, because otherwise it would grow kind of endlessly.
Yeah.
If I may follow up. So that means if I'm still looking for some friends who I do not know whether they have onboarded yet, and I just re-upload all of my contact list basically, and everybody does this, then the cleaning out only helps somewhat, question mark?
Yeah, kind of. You'd hope, firstly, that people don't have a crazy number of contacts. And secondly, that, yeah, a lot of them will be signed up already, so you don't need to query them again.
Thank you.
Great, lovely. Maybe we have time for one more quick question, if there are any more.
Hello.
How are you?
If anyone have access to both of the public keys share in the database and another one in the bullet, and if they monitor all of the data shared by the users, are there any way if they can re-identify who published the data?
No, and that's sort of the crux of these security proofs, is that all this traffic, all these transcripts that we post onto the bulletin board are indistinguishable from random. Even if you've observed the set of public keys, even if you've observed a bunch of shared keys, and even if you have like as many users as you want. Like you can control as many users as you want as an adversary, you still won't learn about what's happening on the bulletin board.
Yes, thank you.
Great, lovely. We'll stop it there, but obviously Nico's around if you have any more questions. Thank you very much, Nico.
Thank you.
Great talk.